Hi students, in this lecture we are going to learn one of the important concept in the complex numbers is rotation of complex numbers. Okay, rotation of complex numbers. For this one, consider a complex number in organ plane. Okay, organ plane is taken to the real part of a complex number to the vertical axis is imaginary part of a complex number. Okay, let I am considering which is a complex number as z1, then I am considering in the organ plane as a p. Okay, then I can write as p of z1. Okay, so from the concept, from the origin, which is the position vector OP, the position vector OP, okay, the position vector OP is making an angle in an anti-clockwise direction as theta 1, as theta 1. Okay, so now if I consider having the same radius another complex number as q of point q, and the complex number is z2, point q and complex number is z2. Now the angle over here from point, what is point p to point q, the angle over here it is theta 2. Okay, the next another complex number I am considering, which is as a point p, sorry, point r of the complex number z3. Okay, point r of a complex number z3 and from the origin. Okay, now which is making an angle from the point q as theta 3. Okay, from the point q as theta 3. Okay, so the case we are considering here, it is as all the complex numbers, that means the radius here I am considering this is as radius r. Similarly the OQ is also having the radius r and OR is also having the radius r. Now the case we are considering it as the three complex numbers. Okay, the first case having equal lengths. Okay, having equal modulus. Okay, that means OP or having equal radius also. Okay, having equal radius, then what it is, OP equals to OQ equals to OR, which is the condition we are considering. So that means we can write it as OP is as modulus of z1, which is equals to mod of z2 and which is equals to mod of z3. Okay, in this condition we know a complex number can be written as in Euler's form as what it is, r into e power I theta. Okay, or into e power I theta. Now the complex number z1 can be written as complex number z1 is nothing but which is equals to OP in the form of a vector. We can represent as a vector OP vector, which is equals to z1 equals to having r as a magnitude and the direction, in which direction it is rotating, with the angle of theta 1, then I theta 1. Okay, we can write as OP equals to r times of e power I theta 1. Now what we can write it as z2, that means OQ equals to, okay, then which is equals to z2. Z2 is obtained. Now the total angle, so from the total angle from the real axis, the total angle which is the 1, that means theta 1 plus theta 2. So we can write it as z2 equals to r into e power, the angle can be written as theta 1 plus theta 2. Okay, which can be written as r into e power I theta 1 into e power I theta 2. Okay, e power I theta 1 into e power I theta 2, where r into e power I theta 1 can be written as z1. Okay, z1, r into e power I theta 1 can be written as z1 into e power I theta 2. So the complex number z2, okay, the complex number z2 is obtained, okay, complex number z2 is obtained rotating, okay, rotating z1 with an angle of theta 2. Okay, rotating z1 with an angle of theta 2. Now similarly we can write it as or. What we can write it as or equals to, which is nothing but from the origin real axis, positive real axis to complex number r. What is the angle? It is totally theta 1 plus theta 2 plus theta 3. Okay, so we can write it as r into, now from the positive real axis, this is the one positive real axis, we can write this length as r. Okay, from the origin, r into e power iota times of theta 1 plus theta 2 plus theta 3. This is the total angle, theta 1 plus theta 2 plus theta 3, where we can write this is as r into e power iota times of theta 1 plus theta 2 into, we can write as iota power, so what is e power iota theta 3, where r into e power I times of theta 1 theta 2 can be written as z2. Okay, z2 into e power I times of theta 3, which is the or which is nothing but the complex number z3. The or is nothing but the complex number z3, and we are writing it is as z3 equals to, okay, z3 is equals to, what it is, z2 into e power I times of theta 3. So that means it is clear that the z3 is obtained. Okay, now here we are having z2. If we rotate the z2 with an angle of theta 3, if we rotate the z2 with an angle of theta 3, we will obtain the, what it is, we will obtain the z3 complex number. So now we can write this is as, where z3 is nothing but obtained, our required complex number. Okay, where z2 is the rotating complex number, rotating complex number. So now if we rotate the z2, okay, we are having a z2 over here. If we rotate the z2 with an angle of theta 3, okay, with an angle of theta 3, we will obtain z3. Okay, are you getting? If we rotate the z2 with an angle of theta 3, we will obtain the z3, and we are considering the rotation in the anti-clockwise direction, it will be the positive. Okay, it will be positive. If the same thing can be written as from this one, what is z2 can be written? The z2 can be written as, now the z2 can be written as z3 by e power iota times of theta 3, which is equals to, we can write it as z3 into e power minus iota times of theta 3. Okay, we can write it as z2 equals to z3 into e power minus iota times of theta 3. So where we are having, just I am considering the case. So here the point is z2. Okay, here the point is z2, which represented with q, and here the another point, what is z3, we are representing with r. Now the angle is, so what it is, to obtain the z2 from the z3, so in between, now it has to be in a clockwise direction with an angle of theta 3. Now we have to rotate in an angle of theta 3. So first we need to write it as in the rotation. So the LHS must be the obtained, what is our required, obtained complex number equals to rotating, okay, rotating complex number into exponential of what it is, the angle, what it is, some angle theta. If theta is in anti-clockwise direction, the theta should be taken as positive. If the theta is rotated in a clockwise direction, the theta value should be taken negative. So this is the way of rotating a complex number of equal lengths, rotating a complex numbers of equal length. And we can term it is as, okay, we can term it is as rotating, what we are rotating, rotating Z3, rotating Z3 over Z2. Z3 is rotated to get as Z2. If in the anti-clockwise direction, we can write this is as Z2 equals to, we need to anti-clockwise direction means, okay, anti-clockwise direction means we need to obtain the Z3. Okay, anti-clockwise from the Z2 to we need to move here. Z3, obtained Z3 equals to Z2 into e power iota times of theta 3. E power iota times of theta 3. So that means Z2 is rotated. Rotating this in terms of watts, we can say it is as rotation of Z2, rotation of Z2 to get over the Z3, to get the Z3, rotation of Z2 to get the Z3. Now which can be, this one can be written as rotation of Z3, rotation of Z3 over Z2. To obtain the Z2, we are rotating the Z3. To obtain the Z2, we are rotating the Z3. The theta is positive means we are rotating in anti-clockwise direction. If the theta is negative means we are rotating in clockwise direction. Okay, now this is of having the equal lengths. Okay, having the equal radius, the complex numbers having the equal modulus. Now moving for the case 2. Now the case 2 is complex numbers. Let I am considering a complex number over here, okay, which is equals to what it is, a times, let I am considering here a is a point, another point is b, and I am considering the another complex number over here, it is as c, and now we are having in this direction. So a is a point of z1 and b is a point of z2 and c is a point of the representing the complex number z3. Okay, now we need to rotate this complex number, that means this vector AB, to obtain in with an angle of theta 1 to obtain the AC. Okay, so I am writing it is as rotation of AB. Okay, rotation of AB over AC. We need to rotate the AB to obtain the AC. Just applying the vectors concept, we can easily understand this. Okay, so we can write this is as what it is, rotation of AB. AB can be in the vector it as OB minus OA. Okay, OB minus OA, which is the one, and AC can be written as OC minus OA. So each complex number is represented by a position vector. Okay, position vector. So A represents the Z1 and B represents the Z2, C represents the Z3. Now we are going to obtain AC. That means we can write it as AC equals to, what is the rotation? AB is rotated. AB is rotated, okay, with an angle of anti-clockwise direction, then e power I times of theta 1. Okay, AC equals to, we are rotating AB. Okay, the AB is rotated to obtain the AC. Okay, to obtain the AC. Then in the rotation, we need to write it as obtained equals to rotation of the number with an angle. So obtained AC can be written as OC minus OA. What is OC? Z3 minus Z1. Okay, Z3 minus Z1, which is equals to OB. Okay, some AB. AB equals to Z2 minus what it is OA, Z1. Z2 minus Z1. Okay. Okay, these are rotated with an e power I theta 1. But here the lengths of AC and AB are different. Then we need to consider the unimodular complex number. That means which is like a, if having the vector of length some m length, okay, which is multiplied by the unit vector, vector a by modulus of vector a. Similarly, now it has to be, to obtain the different lengths we need to consider a unimodular complex number. Complex number is divided by its modulus, then we can write it as a unimodular complex number, which is nothing but z2 minus z1. Okay, if the complex numbers having the different magnet modulus or different radius, then we can represent as what it is, z3 minus z1 by mod of z3 minus z1 equals to z2 minus z1 by mod of z2 minus z1 into e power I theta 1. Okay, now if the AC is rotated, okay, now the AC is rotated, a point of complex number represents the complex number z1, C a point represents the complex number z3, and B a point represents the complex number z2. Now rotate AC to represent AB. So AC has to be rotated in what it is, clockwise direction. If it is rotated in clockwise direction, the theta must be considered as a negative. Now over here, so we are rotating AB. Okay, rotation AC to obtain what it is, AB. Okay, we can write it as, what is our obtained equals to AB equals to rotating AC. Okay, rotating AC into e power in the clockwise direction minus I theta, e power minus I theta. Now which can be written as, okay, which are written as AB equals to OB minus, okay, OB minus OA. OB is nothing but the complex number Z2 minus Z1. OA is Z1. Now these are of different lengths, then it must be taken as a unimodular complex number, which is equals to AC, OC. Okay, OC, that means is nothing but the position of complex number Z3 minus Z1 by modulus of Z3 minus Z1 into e power minus I theta. Why? Because now we are rotating in clockwise direction. In the clockwise direction, the theta is negative. So this is the way of representing the rotation of complex numbers. Now again considering AB is rotated to obtain the Z3, and the theta argument can be written as, what is argument? Theta equals to the angle BAC, which can be written as arg of, okay, now how to write the argument? BAC. Okay, so that means Z2 obtained, what is the we are obtaining? We are rotating in anti-clockwise direction, obtaining it is as AC. Then in the complex number, the obtained AC is the OC minus OA, that means Z3 minus Z1. And what is the vector we are rotating? AB is rotating, then we can write it as AB is rotating, then AB vector can be written as OB, that means vector Z2 minus Z1. Okay, Z2 minus Z1. So the argument can be written as arg of obtained by the rotating. Obtained, what is obtained here? Over here it is AC is obtained, then we are writing it as Z3 minus Z1 by, and rotating we are AB is rotated, then we can write it as Z2 minus Z1. Okay, so arg of Z1 by Z2 can be written as arg of Z1 minus arg of Z 2, then we can write it as arg of Z3 minus Z1 by Z2 minus Z1. Okay, which is, so in this one the argand can be written as argand of obtained by rotating, then we will get the required argument of the rotation of the complex numbers. I think you understand the rotation of the complex number. If a complex number having the Z1 is rotated to obtain the Z2, okay, to rotate it to obtain the Z2, we can write it as that obtained equals to, okay, obtained equals to what it is, rotating with an angle. Z1 is rotated with an angle theta 1 in anti-clockwise direction. If Z2 and Z1 are having the equal modulus or equal radius, if these are of different radius, we can write it as Z2 by mod Z2 equals to Z1 by mod Z1 into e power I theta 1 if it is in anti-clockwise direction, and if it is in clockwise direction the thetas are should be considered as a negative. Okay, now we will understand the rotation of complex numbers with this example. The question is given that if Z1, Z2, Z3, Z4 are vertices of a square taken in anti-clockwise direction, show that 2 times of Z2 equals to 1 plus I times of Z1 plus 1 minus I times of Z3. Okay, now here I am considering a square, okay, having the vertices as, so I am considering this is a point A having the vertices as Z1, and this is point B having the vertices Z2, and taken in anti-clockwise direction, that means this is the rotation anti-clockwise direction, then we will get point C represents the complex number Z3 and point D represents the complex number Z4. Okay, these are taken in anti-clockwise direction, then show that, okay, so that means here we are considering AB is array and AC is another thing. Okay, now consider in particular order. Now if to BC is rotated, now I am considering rotating BC, anyone, you can consider anyone in an anti-clockwise direction. Now I am considering rotation of BC. Now I am rotating BC to get, okay, to get what it is BA, okay, to get BA, so the direction must be clearly mentioned to get the BA, not AB. Now I am rotating AB to get BA. So to get BA, now this has to be rotated. Okay, now the BC has to be rotated with an angle of pi by 2. Okay, with an angle of pi by 2 in anti-clockwise direction. Now you can consider anyone. CD. Okay, now if we consider the CD to get, if we rotate the CD in this direction, okay, but it is in the anti-clockwise direction, you need to consider in the anti-clockwise direction, okay, to get the BC or CB, okay, consider in any direction. Okay, so now what I am considering, BC is rotating to get it as BA. So what is we are obtaining? BA, the obtaining BA can be written as rotating BC into e power anti-clockwise direction, the angle is pi by 2. Okay, the angle is pi by 2. Then what is e power pi by 2, which is equals to cos pi by 2 plus I times of sine pi by 2. Okay, cos pi by 2 is 0 and I sin pi by 2 is 1. Then e power I pi by 2 results as simply I. Then BA can be written as OB minus, sorry, OA minus OB. Okay, position vectors OA minus OB. Then OA minus OB means OA is Z1. Then we can write which is equals to Z1 minus Z2 equals to, and what is here, OC Z3 minus Z2. Okay, BC OC minus OB Z3 minus Z2 into e power I pi by 2, which is nothing but simply I. And here the Z1 minus Z2 lengths, it is a square, the lengths all are equal, having the equal, then you do not divide with the modulus of this complex number, just simply consider Z1 minus Z2 equals to Z3 minus Z1 into I. Okay, now simplify this. What we'll get over here, Z1 minus Z2 equals to, we will get it as Z3I minus Z2I. Okay, so write it as what it is. I'm moving this Z2I to the LHS, moving the Z2I to the LHS. Why we are having Z2 terms over here. Then I can write it as Z2I minus Z2 equals to Z3I minus Z1. Okay, Z3I minus Z1. So from the LHS, we can take Z2 as a common, then we can write it as I minus 1 equals to Z3I minus Z1. Okay, Z3I minus Z1. And we can write it as Z2 equals to Z3I minus Z1 by, and we are having here minus 1 plus I. Okay, now which is in the form of some division rule, Z1 by Z2. So in order to divide, the numerator conjugate has to be taken, then minus 1 minus I, then minus 1, the conjugate is minus I, the conjugate of minus 1 plus I is minus 1 minus I, and if we take minus as a common over here, we will get it as a 1 plus I, and in the denominator also if you take minus as a common, 1 plus I, and this will minus will be cancel out. Then try to simplify this. Z2 equals to what it is, Z3I times of multiplied with cross multiply I plus 1, I plus 1, Z3I times of I plus 1. Next minus Z1 times of what it is, I minus plus I minus 1. Okay, it is multiplied by plus I minus 1. Okay, plus I minus 1, and what it is over here, 1 plus I, that means I plus 1 into I minus 1. Okay, if we simplify this, what we'll get over here, Z3 into what it is, I into I square, that means minus 1. Okay, plus I and minus Z1 times of iota minus Z1. Okay, minus Z1 times of iota minus Z1. Okay, here it is multiplied by simply I plus 1 only. I plus 1 we will get. Okay, why? Because I plus 1 is multiplied this one. Okay, in the denominator we will get it as a minus 2. Okay, in the denominator. So a is I plus 1 into I minus 1, a square plus b square. Okay, now a square is minus 1, sorry. Okay, we will get it as a minus 2 over here. And what it is, we can write it as Z2 equals to, okay, 2 times of Z2. If we cross multiply, we can write a 2 times of Z2 equals to minus of, and I can multiply this as minus Z3 plus Z3 times of I minus Z1 times of I minus z1, okay, which is equals to what it is, z3 minus z3 I plus z1 I plus z1. And if we take z1 as a common from these two, we can write it as I plus 1 times of z1. And if we take z3 as a common, then we can write as 1 minus I times of z3, which is equals to 2 times of z2, which is our required condition. Okay, which is our required condition. Okay, so this is the way of using the rotation of complex numbers whenever the vertices and all the given conditions are given. Okay, thank you.